Hi everyone, my name is Jiaqi. I'm from the Ohio State University. Today I want to present our work, Enabling Parallel Channel Estimation with Commercial Passive Backscatter Tags. RFID stands for Radio Frequency Identification Device. One RFID tag only costs 5 to 10 cents. Hence, they have been extensively used in building low-cost sensing systems such as smart homes, healthcare, and so on. Collision caused by simultaneous tag responses is one of the key issues in RFID systems. The reader initiates an inventory run by sending a query command. The tags will randomly choose a time slot to respond to RN16 package without coordination, thus making the collision an inevitable issue in RFID systems. Previous MacLear solutions usually design new access mechanisms for RFID systems. However, such solutions become expensive to achieve since they rely heavily on systems management infrastructures and computational assumptions. So, there is a growing interest in physical layer solutions as they do not rely on those things. Some anti-collision approaches have been proposed in recent years. Such approaches enabling parallel decoding using the collided data. However, such cluster-based approaches have two drawbacks. First, they can only support 3 to 5 tags, as shown in the figure. When the number of tags increases, it is very hard to separate all clusters. However, in most sensing systems, they require a larger distribution of tags. Also, the anti-collision methods are designed for communication systems, not sensing systems. They require to change the procedure of communication, where the tags need to transmit the EPC packets simultaneously, which means that such systems cannot work for the commercial tags. Most RFID-based sensing systems capture the changes of environment by measuring the channel fluctuations of tags. The main purpose of sensing systems is to measure the channels rather than decoding. Hence, our core idea is to acquire the channels of all the collided tags and match the channels to the corresponding tag without decoding. In this way, we can enable parallel sensing for the commercial RFID systems without any modification on the tag set. We present a parallel sensing scheme, COFFEE, which is short for collision-free RFID-based sensing. COFFEE collects the raw samples from the receiving antenna and recovers the missing channel information from the collision data. In this way, we can get the channel information of each tag more frequently and thus increase the fidelity of the sensing systems. Our system can work as an extension to the current standard, which is compatible to the C1G2. So our system can assist all the RFID-based sensing systems that utilize the fluctuation of channel information. The figure illustrates the detailed workflow of COFFEE. Due to the time limitation, we will go through the design of channel extraction and the tag identification. We first describe the key observations which support our idea and then introduce the details of the design. Our first observation is the various response delay. The response delay is defined as the time interval between the reader's query command and the tag's RN16. The length of response delay is determined by many factors such as the locations, the manufacturer, and so on. Such variation of response delay can be captured by the reader because the reader usually has a much higher sampling rate compared to the RFID tags. Our second observation is the stable bit duration. The bit duration is defined as the time for one tag to send one bit. For one tag, the bit duration is only determined by its clock, and the clock is only related to the environment factors such as temperature and moisture, which does not change across the time or space. The figure shows that the average fluctuation of the bit duration for one tag is within 0.4 milliseconds, which is only 4 samples when the sampling rate is 10 MHz. Our third observation is the continuous channel change. The channel of one tag is defined as the channel between the tag and the reader in time domain. Typically, the channel of one tag usually changes within some range during the coherence time. The figure illustrates the change of one text channels in time domain. Even when there exists human activity between the tag and the reader, the adjacent channels still change within some range. Then we describe how we extract the channel of multiple tags from the collected data sequentially. Our core idea is to separate one data stream from the collected tags based on the order of arriving tag and cancel the transmitted data of this tag after channel estimation. Then we repeat this procedure until all the collected data is subtracted. Based on our first observation, the signals of different tags usually arrive with different response delay. This figure illustrates the procedure when multiple tags join. Before the data stream of the first tag arrives at the reader only receives the 0 bits. After one tag joins, the signal steps to non-zero bits, and when the following tag joins, the level of the non-zero bits changes. Hence, we can obtain the clean channel of the first tag, since there must exist a time when only the first tag is transmitting. After getting the channel of this tag, we need to identify the tag. Traditionally, the tag ID can be decoded from the EPC message. Hence, in our system, the goal is equivalent to acquiring the corresponding tag ID without decoding. Due to the channel fading and multipass effect, the channels between different tags and the reader are different. Hence, we can use the channel information as a fingerprints of the RFID tags to identify them. Although the channels can be viewed as continuous changing within a short duration, due to the dynamics of various links, the channels can vary a lot beyond the coherence time, especially for sensing systems where the objects keep moving all the time. To tackle this issue, we propose a weighted streaming nearest neighbor classification algorithm as summarized here. The different channels will have different weights based on the timeline. In this way, we can identify the tags based on the extracted channel and the history channel information even when the channels change over time. Since the preambles of the RN16 are predefined and the channel of one tag is known at this time, the data that transmitted of one tag can be predicted and extracted from the residual data. The figure plots the procedure of canceling transmitted signal of one tag one by one. By repeating the previous procedure, we are able to recover the channels of all the collected data and identify them. To evaluate coffee in practice, we build a prototype and run experiments in the real world. We build the prototype using commercial UHF tags and the software-defined reader. Then we ran some macro benchmark experiments to validate the components of coffee separately. In this section, we investigate how efficient coffee can separate and extract the channels from collision when the number of tags increase. The results indicate that our system can extract more channels when the number of collected tags increases. Previous work can only support 3 tags simultaneously transmitting. In our system, even when there are 8 tags, we can still obtain sufficient channels from collisions. Since our scheme can allow more tags to transmit simultaneously, the tags can transmit more frequently, which means that our system can get much more channels. In this part, we do experiments to evaluate the channel estimation accuracy. The results indicate that error remains relatively low even when 8 tags collide. In this part, we evaluate the accuracy of our tag identification algorithm. The results show that our identification algorithm can still achieve a high prediction accuracy up to 0.993. To evaluate the benefits when deploying multiple RFID tags, we measure the average time resolution gain of coffee over C1G2 with system-level tests. We run experiments with 4 to 16 tags being employed. We can see that the median gain with 16 RFID tags is around 3.42 times on average. In this paper, we propose coffee, the first system that can harness the collision to improve the fidelity for sensing systems using commercial tags. Coffee can be treated as an extension to C1G2 standard, and which can be applied for all the RFID systems without modification of the tag set. These are the related works that we refer to. Thank you.